All right, let's jump right into a paper from way back in 1989. Now, on the surface, it's about teaching a computer to read zip codes. You might be thinking, zip codes, how exciting can that be? But stick with me here, because what this paper is really about is a revolutionary idea that completely changed how we build AI. This isn't just about sorting mail, it's basically the origin story of modern computer vision. So I want you to transport yourself back to the late 80s. There's no email, not really. There are just mountains and mountains of physical letters. And the US Postal Service had this just astronomical problem on its hands. How do you sort all this mail with messy, handwritten zip codes? This wasn't some theoretical thing in a lab. It was a massive, real-world headache that was slowing everything down. And that leads us to the billion-dollar question, right? How on earth do you teach a machine to do something that feels so uniquely human? How do you get it to see the patterns in the absolute chaos of our handwriting? I mean, just look at this stuff. This is what the researchers at Bell Labs were staring at every single day. The paper literally describes it as coming from many different people using a great variety of sizes, writing styles, and instruments. We're not talking about crisp, clean numbers here. They're smudged, they're slanted, they're all run together. To be honest, some of these even a person would have trouble reading. Now, the old school approach to a problem like this was basically to just throw a bigger computer at it. More horsepower, a bigger hammer, hoping you'd eventually crack the nut. But the team behind this paper knew that was a dead end. The answer wasn't going to come from more brute force. It had to come from being smarter. And this is where they had their big aha moment. What if instead of starting the computer with a totally blank brain and hoping for the best, you gave it some clues? You could actually embed knowledge about the world right into its design. They basically looked at how our own brains process vision and decided to, well, copy that blueprint. And their entire approach really boiled down to these three brilliant ideas. First up, don't try to see the whole number at once. That's too hard. Instead, just look for tiny, simple things, little lines, curves, corners. Second, and this is the real game changer, realize that a little curve is still a little curve no matter where you find it in the image. And third, as you go, you gradually shrink the image, which makes the network care less about the exact location of those features. So how they actually do this? They invented something called feature maps. The best way to think about these is like a team of super specialized detectives. You've got one detective whose only job is to scan the image for vertical lines. That's it. And another detective whose entire life is dedicated to finding curves in the top left corner. Each map is looking for one specific clue. Okay, so you've got your team of detectives, but how do you make sure the vertical line guys are all looking for the exact same kind of vertical line? Well, you use a trick called weight sharing. It's pure genius. It just means that every detector on a single map is forced to use the exact same set of tools. It's like you give them all an identical magnifying glass. This not only makes them learn the same thing, it's also wildly, wildly efficient. All right, so we've got the big idea, the philosophy behind it. Now let's pop the hood and see what this thing actually looked like on the inside. What does a neural network with geometric knowledge baked right in really look like? So here's the journey a little handwritten number takes. It starts as a tiny 16 by 16 pixel image. First, it hits layer H1. That's our team of detectives, the feature maps, finding all the basic clues, the lines and curves. Then, layer H2 acts like a lead detective, taking those simple clues and starting to piece them together into more complex shapes. Finally, after all that, the last couple of layers look at the big picture and make a call. You know what? Based on all the evidence, I'm pretty sure that's a 4. Now get ready for this. If you were to count every single connection between all the neurons in this network, you would get this number. Over 64,000. And for 1989, that is just astronomical. So you might be thinking, wait a minute, I thought this wasn't about brute force. Well, that's the magic. Because of that brilliant weight-sharing trick, the network didn't have to learn 64,000 different things. It only had to learn this many, less than 10,000. All those other thousands of connections were just copies, using what it had already learned. And that's the punchline right there. A nearly 7 times drop in the number of things the network actually had to figure out for itself. It's so elegant. By building in that one simple idea, that a line is a line no matter where it is, they made a system that was incredibly powerful, but also incredibly efficient. It's the difference between being big and being smart. Okay, so the theory is beautiful, the design is clever, but does it actually work? I mean, that's the real question. So to find out, the researchers set up a head-to-head competition. Their new smart network versus a more traditional, dumber network to see which was actually better at the job. So you've got two totally different philosophies here. In one corner, you have the new idea, the constrained network, our team of specialists. In the other corner, you've got the old way, the fully connected network. That's the brute force method. Just connect everything to everything and hope for the best. It's elegance versus raw power. And the winner was, well, it wasn't even close. When they showed both networks brand new digits they had never seen before, the brain-inspired network blew the old one out of the water. It was just way more accurate. That built-in knowledge meant it could handle new, weird handwriting much, much better. But hold on a second. A 5% error rate might sound pretty good, but for the post office, that could mean millions of letters going to the wrong house every single day. No way. So being right is great, but what's even more important for a real system is knowing when you might be wrong. And this next part is maybe the most impressive results in the whole paper. The team figured out a way to get the error rate all the way down to a stunningly low 1%. So how on earth did they do that? Simple. They taught the network how to say, I don't know. Seriously, they set a confidence level, and if the network saw a digit that was just too weird or smudged and it wasn't sure, it wouldn't guess. It would just reject it and flag it for a human to look at. That one little feature, the ability to admit confusion, is what made it truly practical for the real world. So yeah, they solved the mail sorting problem, but the story doesn't end there. In fact, that's really just the beginning. What this paper really did was create the blueprint for, well, for pretty much everything that came next in AI vision. Remember those three guiding principles we talked about earlier? Local features, weight sharing, and subsampling? Well, that's it. That is the fundamental DNA of what we now call a convolutional neural network, or a CNN. It is the absolute bedrock of modern computer vision. Think about it. Every time you unlock your phone with your face, that's a CNN. Every time AI helps a doctor spot a tumor on a scan, that's a CNN. Every time a self-driving car spots a pedestrian, yep, that's a CNN too. All of these incredible technologies are the direct descendants of the ideas tested on those messy, handwritten zip codes. And this quote from the authors themselves just nails it. The breakthrough wasn't just better hardware or more data, though that helps. The real breakthrough was a shift in philosophy. It was about consciously designing a network to understand the basic rules of the world it was looking at. So let's just end on this thought. The profound lesson from this incredible 1989 paper is that intelligence isn't just about raw learning power. It's about having the right structure to learn effectively. This principle solved the zip code problem and literally gave computers sight. So the question for us today is, what other monumental challenges are out there, just waiting for us to solve them, if we just start by baking the right kind of knowledge in from the start?